Okay, I wanted to talk a little bit about the exam. The third exam will be taken during finals week, during the regularly scheduled finals time, which for us, for controls, is going to be Monday, May 11th, from 2 to 3:50, 2-hour block. It will be a closed book exam, one-page handwritten notes. You will be expected to use MATLAB, and you will be allowed to use MATLAB for this. And the completed exam will be submitted on Canvas and PDF and MATLAB files. Had some issues with this last on exam 2. There were a number of you that had trouble with the MATLAB files and also with the scanning. So take some time, figure that out before the exam. I think I'll do it a little bit differently this time. Probably the PDF will be a single document that you will submit, and then the MATLAB files will be submitted. Probably have to submit those separately, but I'll look into that and let you know what's happening with that. So, as far as the content for the exam, it's going to be focused on the frequency response. Okay, the content since the last exam primarily. Be talking about Bode and loop shaping and those kinds of things. So don't expect a lot from the first part of the class, the content from the first two exams. Yet they're fair game. They're fair game. If I talk about something, I expect you to understand what I'm talking about. It probably won't have any problems associated with, no root locus, no, and I'm not going to have a modeling problem on this exam. And so it's going to be focused on the frequency response. And you'll need to understand the idea of the frequency response. We're putting in a sinusoidal into our system and looking at the response out of the system and plotting that both in phase and magnitude. And as opposed to putting in an impulsive step, primarily a step, and looking at the response from the roots. So you need to, in concept, at least to understand what the difference is on that. We'll expect you to be able to calculate the magnitude ratio and the phase shift for a specific frequency. We did a homework on that, and obviously the Bode plot, and what it is, how to sketch it. There will be a sketch problem, or at least one sketch problem. Understand the idea of bandwidth, crossover frequency, and phase margin, gain margin. Okay, bandwidth, remember, comes from the closed loop and is closed loop Bode at where the magnitude plot crosses minus 3 dB. The phase margin, gain margin are from the open loop, and the phase margin is found at the crossover frequency. The gain margin is found at the minus 180 crossover frequency. And so be able to identify those and find the magnitude of those on a typical Bode plot like we did in the homework. Understand what the ideal closed loop Bode looks like. And if you remember, we talked about this, the magnitude plot and the phase, magnitude and phase. And for the ideal Bode plot for magnitude would be a straight line at 0 dB, and phase would be a straight line at 0 phase. If our output matched our input exactly, that would be the ideal, and that's what we were shooting for as we started looking at the loop shaping of that. How do we modify the open loop shape of the Bode to get the closed loop Bode to what we want it to be? And the way we did that, we talked about the open loop Bode as being, let me see if I've got this, loop shaping. We talked about the open loop. We want to push it up in the lower frequencies, down in the high frequencies, and through the crossover frequency, we want it to be minus 20 dB per decade. the open loop, pushing it up on the low frequency, gets us better tracking of there, and we follow the signal more accurately with higher fidelity. The down on the high frequency, we attenuate any of the noise or any of the signal that we can't control, that's not doing what we want it to do. We want it to go away, to be attenuated. And then the minus 20 dB per decade across the crossover frequency, we accomplish that by we want to maintain our phase margin with that, because our phase margin would be 90 degrees or minus 90 degrees at that. And so with those three parameters in there, and we shape that with our tools, our zeros, poles, and gain, we can reshape the open loop to give us the best closed loop for our application. And so want to make sure about that. Sorry, wrong one. Okay, so understand the shape of the open loop Bode that impacts the characteristics of the closed loop Bode. And so then we move on to the loop shaping. We actually jumped the gun on that a little bit. We want to think about loop shaping and what we want to do, as I described before, and how we use our tools, our gains, our poles, and zeros to reshape it. Remember, our gain, we move the magnitude plot up and down with our gain. Our poles will drive the magnitude plot down by 20 dB per decade. And their zeros, we can lift them up, change the slope by 20 dB per decade. So we can reshape that with our gains, poles, and zeros. Remember the performance specs on here, and I've got a little bit of that also in the next topic. We use our two ways to determine, or at least in this class, what we're using is two ways to determine our crossover frequency. One is by performance specs. We have a performance, an omega C that we are desiring, and we get that omega C from our time domain response specifications, our rise time, or settling time, peak time. And so we have a crossover frequency that we're trying to accomplish with that. And so we can set our crossover frequency. The other way is with high frequency. If we know we have some high frequency out there at a specific frequency, and we know that frequency, then we can back 10 times off of that 1 decade, and that's where we're going to place our crossover frequency. So two different ways of doing that in our loop shaping. Once you have your controller designed, then I want you to be able to go from a transfer function, a ZPK form, to a KP, KD, KI form, okay? Because our controllers typically ask us for a KP, the gains, the KP, KD, KI, but we work in our analysis and design in terms of zeros, poles, and gains. And so we need to be fluent at moving back and forth between those two. Of course, this next topic comes up. We studied this a while back, but it still is relevant, especially in the loop shaping. And so I never tested you on that, so I'm going to put that on the exam. Be able to the Bode plot from experimentation. We created a Bode plot in lab. We subjected the motor lab to different frequencies and looked at the magnitude and the phase shift and plotted that, and be able to calculate. That's a repeat from earlier, and this is a repeat also, being able to calculate that. You will be able to, need to be able to use SISO tool. This is going to be a really nice, handy tool for you. And my expectation is that you will be given a system with some specifications and asked to do loop shaping, and that is a task that is done very easily in CysoTool. So become fluent in CysoTool. Know some of the commands: Bode, margin, pzmap, zbk, step, all the commands we've been using in lab and in homework. Be able to use them fluently, write scripts, live scripts for this, and work the problem. So my expectation, I'm going to try to make the exam a little bit shorter, so that you have time to deal with all the issues that are going on with this. We will do the whole thing in 1 hour and 50 minutes and submit it on Canvas. And so that is the topics for the final exam, the third exam.